Hey everyone, welcome back. In the last episode, we built functions to load and analyze our dataset, including parsing each row, mapping labels into collision or no collision, and even printing the class balance. But before we can actually train a neural network, we need to prepare the dataset properly. That means two things. First, we need to split the dataset into a training set and a test set. The training set is what the neural network learns from, while the test set is kept aside to measure how well the model generalizes to new data. Second, we need to shuffle the dataset. If we feed the data in its original order, the neural network might learn unintended patterns like the sequence of the dataset, instead of the actual sensor features. Shuffling ensures the samples are mixed randomly, making training more robust. In this episode, we'll implement the loadAndSplitSensorData function, which loads the dataset, shuffles it, and then splits it into training and test sets. Let's get into the code. We start by defining a new function, and this is a long signature, but it's straightforward. Let's see. Bool load and split sensor data. And we pass in the dataset file name, const std string reference file name. Then we provide separate containers for training features, labels, and IDs. std vector, double, reference, training underscore features. And std vector, double, reference, training underscore labels. And std vector, int, reference, training underscore IDs. And the same for the test set. std vector, double, reference, test underscore features. And std vector, double, reference, test underscore labels. std vector, int, reference, test underscore IDs. And we also allow a training ratio. By default, 80% training, 20% test. And here we say double training underscore ratio equals 0.8 or 80%. Finally, we pass in a label mapper with a default lambda that maps our labels into collision or no collision. Const std function angle brackets int, and inside parentheses const std string reference, and reference label mapper equals square brackets inside parentheses const std string reference L, and inside curly brackets we return each collision label inside parentheses L question mark 1 colon 0 and semicolon. Inside the function, we first load the entire dataset into memory using the function we built in the last episode. We start by creating 3 vectors to hold all features, all labels, and all IDs. std vector, double, all underscore features. std vector, double, all underscore labels, and std vector, int, all underscore IDs. Next, we try to load the dataset using our loadSensorData function. If not loadSensorData, and we pass in file name all underscore features, all underscore labels, all underscore IDs, and label mapper. And if something goes wrong, we return false. Return false. Now we have got everything in all underscore features, all underscore labels, and all underscore IDs. Next, we want to shuffle everything together. We create an index vector and shuffle it with a random number generator. std vector, size underscore t, indices, and we pass in all underscore features dot size. Then we use std iota to fill the vector with sequential numbers starting from 0. std iota indices dot begin, indices dot end, and 0. So if we have 100 samples, this will generate indices 0, 1, 2 up to 99. This is the same as writing a for loop that assigns each position its own index. Next, we create a random number generator. std empty 19937, and we call it gen, and we pass in std random underscore device curly bracket parentheses, and we call std shuffle to randomly rearrange all the indices. std shuffle, and we pass in indices dot begin, indices dot end, and gen. This way, instead of disturbing the original vectors directly, we shuffle their indices and then rebuild new vectors in random order. We then create shuffled versions of features, labels, and IDs. And here we say std vector, double, features underscore shuffled, and std vector, double, labels underscore shuffled, and std vector int IDs underscore shuffled. Before we start filling these new vectors, we call reserve on each one. Features underscore shuffled dot reserve, and we pass in all underscore features dot size. Labels underscore shuffled dot reserve, and we pass in all underscore labels dot size. And IDs underscore shuffled dot reserve, all underscore IDs dot size. What this does is pre-allocate the required memory for all the elements in advanced. Then we look through the shuffled indices and move each element into the new vectors. For size underscore ti colon indices. And inside the loop we say features underscore shuffled dot push underscore back, and we pass in std move all underscore features square brackets I. Labels underscore shuffled dot push underscore back std move all underscore labels square brackets I. IDs underscore shuffled dot push underscore back all underscore IDs square brackets I. Using std move here avoids unnecessary copying, making it more efficient. At this point, our dataset is fully randomized and ready to be split. Before we do that, it's also a great time to print and log the class balance so we can double check how many collision and non-collision samples we have. So here we say print class balance, and we pass in features underscore shuffled and labels underscore shuffled. Next, we calculate how many samples go into training. Size underscore t, train underscore size equals static underscore cast, size underscore t, inside parentheses, train underscore ratio, times features underscore shuffle dot size. Now we split the dataset into training and test sets. And we do it like this. Finally, we print some statistics so we know how the dataset was split, number of samples, number of features, and so on. After successfully loading, shuffling, and splitting the dataset, we return true, indicating that everything worked correctly and the training and test sets are ready for use. Alright, that's it for this episode. We now have a function that loads the dataset, shuffles it, and splits it into training and test sets. In the next episode, we'll use this prepared dataset to start training our neural network for robot collision prediction. So if you are excited to see that in action, make sure to like the video, subscribe, and turn on notifications so you don't miss it. Thanks for watching, and I'll see you in the next one.